Well, thanks for the introduction and also the invitation to come to Oxford. And I'm very grateful that you accommodate my last-minute remote presentation. I was already sitting at the gate, but then everything got cancelled and apparently very hard to come to London. So before I start talking about aggregating lattice-based signatures, actually have a little bit of storytelling. It would have been such a pleasure for me to stand today on stage in person in Oxford because like 7 years ago, I attended a spring school on lattice-based cryptography, I guess in the very same room. And yeah, it was my very first contact with lattice-based cryptography. And I was there as a master student and it really hooked me up. So I guess at that point, thanks to Ali for having organized the spring school at that time. But now to science. So I want to talk about digital signatures today. As everyone knows, they have been introduced by Delphi and Hellman in '76. And the setting is that we have Alice, who has a message, and then she provides a signature that authenticates that she signs this message. And then we have the rabbit who verifies this signature. And I guess the main motivation of digital signatures is that they want to provide a digital analog of handprint signatures with the hope of maybe being even more secure and coming with more functionalities. And this is really what today's talk is focusing on. So the setting we are in is that we have multiple signers, so we have multiple Alices. And each of those Alices has an own message. So we have also multiple messages, but we have the same verifier. So one single rabbit. And the naive solution would be that every Alice signs the message and then sends it to the rabbit. And then the question we are asking ourselves whether there is a way to make this more intelligent. So to combine the individual signatures into one single, hopefully compact signature. So we want to also be able to scale that up for many more signatures. And this is a concept that has been introduced in the early 2000s by Bonnet, Gentry, Lin, and Shechem, and is called aggregate signatures. So the idea is that I have my three Alices on the left, and I have some magic going on, and then I will have what I have here as a black aggregate signature that accounts for all three messages. And I only have to send one single signature to the rabbit to verify. So there are different models that we distinguish. The original model introduced by Bonnet and co-authors is non-interactive. That means that the three Alices are producing their signatures independently. And then there's some aggregation procedure that can mix those three signatures into a single signature. And we sometimes also call this public aggregation because it doesn't need any secret key material. We can slightly, I guess, weaken the model by requiring that all Alices have access to the same time clock, and that we can only aggregate signatures that have been provided on the same timestamp. So we call these synchronized aggregate signatures. And then another model is that there is some form of interaction, but it's very structured. We call them sequential aggregate signatures. So now the first Alice will sign her message, and then she will send her signature to the second Alice, who will then provide a signature that now accounts for her message, but also the message of the first Alice. And then she will forward, so the blue Alice, we are in the second Alice, will then forward her signature to the third Alice, the red Alice, who now can produce a final signature that accounts for all three messages together. And this final signature will be sent to the rabbit. And then there are also interactive aggregate signatures where all three Alices communicate with each other. And as an outcome of this communication, there will be one aggregate signature. So today I'm actually not so much talking about interactive solutions, mostly about non-interactive and sequential solutions. So when we look at aggregate signatures, we are interested in the compression rate. So that is the quotient between the size of our aggregate signature and the size of the trivial solution of sending all individual signatures. And this compression rate should be much smaller than 1. So let's say our preferable goals are that we want as few interaction as possible, because interaction means parties have to be online at the same time. It also means most of the time some latency. So we really wanted to keep it as non-interactive as possible. And then we, of course, want to reduce the compression rate. And because we're here in a post-quantum workshop, we would like to guarantee presumed post-quantum security. And ideally, we want to aggregate signatures that are going to be standardized. And in particular, I'm going to focus on dilithium and Falcon today. And what I'm less focusing on, but of course should always be kept in mind, is that we also want to have fast signing, fast aggregation, and fast verification. So the research question I come today with is whether we can construct an aggregate signature scheme based on Euclidean lattices. And I brought you 3 answers. So I have let's say a failure that I present, which was a first trial together with Adeline Roulon-Noir, where we non-interactively aggregated the lithium type signatures, but our compression rates are larger than 1. That means our aggregate signature is actually larger than just sending the individual signatures, so completely of no interest. But still illustrative, I think. And then I have a semi-success where together with Akira Takahashi, we managed to get a non-trivial a non-trivial aggregation, but this time we require some sequential interaction. And this is again for the lithium type signatures, but now the compression rates are still very close to 1. And then I have a last result that is luckily a bit of a success, where we managed to non-interactively aggregate Falcon signatures. And this is a joint work with Marius Adal, Diego Arantxa, Sebastian Colby, and again, Akira Takahashi. And this is going to be presented at Crypto. Okay, and this is going to be our plan for today. So I'm going to go through all 3 results. So I guess whenever I'm going into the next part is a good moment also to ask questions. Feel free to interrupt whenever you want. So the failed approach.
All right, there's one question from the...
Yeah.
Can you hear me?
Yeah, you just have to speak loud.
Oh, sorry.
Yeah.
Success, you had this factor of 0.06. Is this as the number of signatures capital N tends off to infinity, or?
Yes.
Yeah, okay.
Yes, yes. I mean, ideally you want, for instance, to have something like logarithmic, no? You want to have the size of the aggregate signature to be logarithmic, then the compression rate would go to 0. And you will see later that we don't have, for specific reasons, we don't have logarithmic asymptotics. So but it's pretty small, so it's good.
Thank you.
Thanks. Okay. So I will start with the failed approach. And for that, I will remind ourselves about the lithium type signatures. I'm assuming some familiarity, so I will be rather quick on it. So as public parameters, we have a cyclotomic ring, a modulus Q. We're working on the random oracle model, so we have access to a random oracle H. And I will assume now that every signing party uses the same matrix A, which will be assumed to be random. And then for the key generation, Alice samples a small vector over the ring. And when I say small, I always mean of short norm. And her public key will then be A times S modulo Q. And then in order to sign, Alice will sample a fresh Y, again, a small vector over R, and compute U as A times Y, which is often called the commitment, and and then use this commitment as an input to the random oracle together with the message in her public key to obtain C, which we often call the challenge. And this is again a small ring element, and this time it's just a scalar. And then she can compute the secret times the scalar plus the Y. And then there needs something to be happen to make the distribution of Z independent of S. So either you do rejection sampling or noise drowning here, but it's not so relevant for what comes next. And then the signature I'm sending is my commitment and my response. And then in order to verify, the rabbit will check that I have the following identity. The matrix A multiplied by the response Z should be the same as T times the random oracle evaluated at my commitment, message, and public key, plus my commitment. And the verifier, the rabbit, also checks that Z is small. So why is that true? Just a quick correctness check here. So if I compute A times Z and I replace Z by the equation I have on the left side, then I can just use associativity and then replace A times S by the definition of the public key and the definition of the challenge, and I'm obtaining exactly what's standing there. So we're happy. And the observation that we have is that if we have two Alices who do this process in parallel and we obtain two signatures, U1, Z1, U2, Z2, then the verification was just a linear equation. And we could hope that we can just add everything together. So that would mean we would add the U parts and we would add the Z parts together. And then the verification would be that I have now the sum of the equations that should hold. So T1, which is the first public key, times the challenge, and T2 times the challenge. And this quickly runs into a problem because how can the verifier actually recompute the challenges if they only have access to the sum of U1 and U2? But the challenges have been derived with just U1 or just U2. And this is a problem that comes up outside of the lattice world for Schnorr signatures as well, for instance. And there are mainly two approaches to this. Either you go for an interactive solution where the two Alices will try to communicate about the U parts. For instance, they could agree on the same U. And the other approach is that you go for half aggregation. So you give up on having something very compact, but just kind of compact. And in that case, you have to send the U parts because they are needed to derive the challenges, but then you can still aggregate the Z parts. And this is a successful approach in the discrete log case. And we thought that maybe we can imitate that in the lattice world. And now it turns out, I don't know if you have seen it, that I actually said that if you have a single signature, you would send the commitment U and the response Z, and then you would have the following verification equation. But in lattices, people very quickly realized that the U is a large vector over mod Q, and C is a small short scalar over the ring. So it's much more beneficial in terms of efficiency to send the challenge and not the commitment. And if you have access to Z, this is equivalent because you can either evaluate the random oracle and check the verification, or you can recompute U using the challenge and then verify that the random oracle computation has been done correctly. And this trick does work super well in single signatures, but you cannot use it if you're aggregating over the Z parts, because if you now have the sum over the Z parts, you cannot recompute the single U parts anymore. And that means that if we have our half equation, we have to stick to this U form of the signature. So we can send the two U's and then we send the sum of the Z's. But in the trivial concatenation, we can replace the U's by the challenges. So we have C1, Z1, and C2, Z2. And here comes the failure. It turns out that the U part is bigger than sending C and Z all together. So I think this would even be true if I just would have one, but I here sketched it for two. So if I have U1 and U2, then this is alone already larger than sending the trivial concatenation. And that means aggregating the Z parts is completely useless here. And I mean, bigger by some factor of 3, 4. Yeah, so we're kind of stuck here. We don't really know what to do. Yeah, we cannot really like leverage the discrete log solutions to the lattice world here. And that would bring me to my semi-success. So that would be the moment to ask questions about the failure. If not, I will continue. So the semi-success is now saying, well, the problem of our failure were actually the U parts. Is there anything we can do to aggregate on them? And I have said that before that, yes, you can do this, but it requires some form of interaction. And our idea is that instead of needing this full interactive model, we can actually do something in the sequential aggregate model. So just as a quick recap, the sequential model said first Alice is signing, sends it to the second Alice is signing and sends it to the third Alice, and only the third Alice is then sending the aggregate signature to the rabbit. And this concept has actually been introduced also in the early 2000s by Lyskanskaya, Mikali, Raisin, and Shachel. Okay, so what can we do with the lithium type signatures with what I said you before? Well, the idea is that the first Alice will compute her signature completely independent of all the others. And then she sends her signature composed of U1 and Z1 to the second Alice. And what the second Alice now does is that she will add as an additional shift the U part of the first Alice when computing her U part. And she will also commit to the Z part when computing her challenge from the random oracle. So these are the only two modifications. The rest is the same. But now she appends the Z elements to the sequential message. And this is needed in order to recover the previous U part. So we are not sending U1 anymore. We only send U2. But the idea is that U1 is kind of given indirectly as the shift of this equation. And then the rabbit, once they obtain U2, Z1, and Z2, they can first recompute the challenge C2 because they have access to all the elements here. And once they know U2, they can recompute the shift U1 by the verification equation. And once they have U1, the rabbit can recompute Z1, which they know have all the information, and then they can check that the original equation is a valid signature. So I've only detailed it out now for two, but you can just continue doing this for many more. And the observation is that, well, I'm just sketching it. I'm not really explaining how we proved it, but the security of the sequential aggregate signature scheme is tightly implied by the underlying signature scheme, where you would stop after one signature. We don't need any forking lemma, but we are in the random oracle model. And now comes the big limitation, I would say, is that we actually cannot make this approach work for dilithium, really dilithium-like it will be standardized, because dilithium has some optimizations on cutting the low order bits. And this does not seem to behave so well with, let's say, at least interactive aggregation. And in particular, there was an interactive solution for dilithium proposed, and we showed that this was completely unsecure. And so as it is right now, our approach does not directly apply to the to-be standardized dilithium. And now, why it's just the semi-success? Well, if you look at the numbers, then the situation is that the sequential aggregation will only have one U part and then the responses. And the trivial solution will have n challenges and the same responses. And of course, there will be some point where our sequential aggregation will be smaller than the trivial concatenation. And this will be roughly reached with like 70 signatures. But what happens is that the compression rate is not very good because the challenges are comparatively small. So the factor they kind of attribute to the linear part of this trivial concatenation is pretty small. So yeah, for 1 million signatures aggregated, you're still at 0.992 compression rate. So the question is whether it really makes sense to do it. Yes, and that completes my 2 not so successful approaches to aggregating lattice-based signatures. And if there are no other questions, then I'm ready to move on to yeah?
Katharina, can I just ask a question? So did you try applying this to half-dense sign, the sequential aggregation?
Yeah, just wait 10 seconds.
All right.
So for the the last part will be on Falcon, but the sequential aggregation, people have tried it. It will, I should have maybe put the related work there already. The thing is that if you do sequential aggregation for hashed and signed signatures in the discrete log world, you're super happy because you have trapdoor permutations and you can do smart things where you kind of iterate over the trapdoor permutation. But over lattices, we only have trapdoor pre-image sampleable functions where domain and range don't match. So you can sequentially aggregate on that, but you will have to append some part of your signature. Again, there will be still some linear dependency because you have to append some information of your signature throughout all the aggregation process.
All right, thank you.
Ask a follow-up question. For
Yeah.
the trapdoor permutation, do you need it for construction or just for the security proof? So can you just rely on permutations for the construction and wish that it's going to be secure?
No, it's the thing why you would love to have permutations is just that you want range and domains to match, because then you will feed the image of the previous person as your pre-image, or the other way around. The pre-image of the previous signer, you will add it to your new image that you are going to invert. So it's not so much about security, it's just about domain matching.
Yeah, that makes sense. Thank you.
Okay, so we come to the last part, and luckily the most successful approach so far. So I guess the insight was that it seems pretty hard to aggregate dilithium. Let's try the other alternative that we have. Let's try it with Falcon. And a pretty high-level recap of Falcon is that I'm again working over cyclotomic rings with a modulus. I'm again in the random oracle model. And now my public key, like Alice's public key, is a randomly looking element H mod Q in the ring. And the secret key will be some associated lattice magic that I'm not going to detail now. And the idea is that for signing, Alice will sample a random salt or seed. It has both names, like some randomness. And this randomness is put into the random oracle together with the message to define a target, which is a ring element. And then Alice can use her lattice magic to kind of invert this T in a specific way, such that it gives out two ring elements S and S prime that are both small. And so her signature will be composed of the salt and the two S elements, S and S prime. And the lattice magic makes that S times the public key plus S prime equals the target. So the rabbit will just verify that this equation is true and that S and S prime are small. And for the correctness, you just have to believe me that lattice magic does the trick. But we are interested in whether it's possible to aggregate this. And at first sight, it actually seems even harder to aggregate Falcon signatures, because at the lithium, we could assume that every signer uses the same public matrix A. And then the verification was a linear function over this A. But in Falcon, every signer has their own H. And this is tightly related to this lattice magic. So we cannot assume that every signer uses like the same H or even a related H. And so it's not clear how you can aggregate over the signatures of different signers. And so the next wisdom I share with you, when tailored aggregation seems difficult, then it's always good to first try generic solutions. I mean, generally you would expect generic solutions to be less good, but if it's the only thing you have, then maybe better try this. And the folklore observation we kind of found out when we were starting our project was when you have a generic argument of knowledge at hand that produces compact proof sizes, then you can aggregate signature. You can use this generic argument to produce aggregate signatures. And I will explain in the next slide how this idea works. And in particular, this folklore observation was proposed for Falcon-like signatures and for Falcon explicitly before. But it was mostly sketched and rarely detailed out rigorously. And the first caveat I want to say here is that this folklore observation is not true for arbitrary signatures. So there are technical subtleties that occur if you mix random oracles with knowledge extractors and additional signing oracles. And this is an observation that dates back to a paper from 2016 from Fiore and Niculescu. And even though they don't detail it out for aggregate signatures, it is also true for aggregate signatures. But good news is that we made the formal proof that this approach indeed works for hashed and signed signatures, and so also for Falcon type signatures. And so our plan to approach this now was, let's find a suitable argument of knowledge applied to Falcon, and let's try to be as rigorous as possible and give some concrete estimates. So this is kind of the goal for the next slides. So I said the folklore approach is to use an argument of knowledge. I think Kahn has also informally introduced an argument of knowledge. I will stay as informal as he was. So the idea is that I have a language L and a corresponding relation R, and my argument of knowledge will be able to convince a verifier that I know a witness for a statement that lies in the language. And this convincing proof will be much, much more compact than just sending the witness. So we don't care about zero knowledge. It's just that I don't want to send the witness. I want to send something that is shorter. And if I now want to apply this into the case of aggregate signature, then I interpret my signatures at my witness. I have as my statement my messages, and the relation, whether a message lies in the language or not, is that I know verifying signatures. So existing is not enough. Of course, for every message there exists verifying signatures, but we want to convince the verifier that we know such signatures. And then the proof that I'm getting out of this general argument of knowledge will then be my aggregate signature. And it works pretty much as you would expect it. Like if you have a complete argument of knowledge, then this gives you a correct aggregate signature. If you have an argument of knowledge that gives you compact proof sizes, then of course your aggregate signature will also be compact and give you good compression rates. And then I guess what the folklore intuition was that if your argument of knowledge is knowledge sound and your underlying signature scheme is secure, then your aggregate signature scheme will also be secure. And yeah, I will not give details of how we do the proof at the end exactly. I just want to say this is really here where the folklore approach was a bit vague and it's actually not true in general. I can have in the knowledge soundness, I will have an extractor, and in the security of the aggregate signature scheme, I will have access to signing oracles, and the combination is like, you have to be careful if you combine those two. But it does work for hash and sign signatures. So the question is now, what argument of knowledge out of the many that are out there do we want to take? And we decided to take Labrador, proof system by Berlins and Seiler from Crypto last year, because it's based on standard hardness assumptions like module sys, but also because the native language of Labrador is really, really well suited to reflect Falcon signatures. So Labrador is an argument of knowledge that works for any NP language, and you can express any language with our 1CS constraints and then translate it to the Labrador native language. But our hope was that we can stay in the native language of Labrador. So how does the language look like that Labrador supports natively? Well, a witness will be a set of vectors over some ring, and we can have up to R vectors, each of them of dimension n. So we call that multiplicity or rank. And our statement will be a norm-bound beta and a family F of functions, where every function is a linear combination of inner products between two witnesses. Or I have R variables, and it will be a linear function between two variables, or the linear combination between one variable with a public vector and some additive shifts. And then the relation we will want to verify is that for every function in this function family, if I evaluate it at my witness, it gives me 0. And the norm of every witness summed up together can be bounded by this upper norm bound. So I guess the important thing is that I have up to quadratic functions and I have a norm bound check. Yes. So why is that now handy to use with Falcon type signatures? Well, this is the slide I showed you before when I introduced the concept. And now the idea would be that, as said, I do my folklore approach, and I set my signature as my witness, and I set my message as my statement. Here I also include the public key. And my relation will be the verification of the signature. So there's a first issue I'm running into, which is that my verification involves an evaluation of the random oracle. So proving something over the random oracle is already a question what that should mean. And in particular, the native language of Labrador would not support this. We also would, one solution would be that you go to heuristics and you replace your random oracle by some concrete hash function, but still it wouldn't be supported by the native language of Labrador. You would have to go through our 1CS constraint system. So we opted to put the random oracle evaluation out of the relation. So what we do is that we append we kind of send the salt in the clear. And once you have the salt and the message, you can compute the target, and that will be part of the statement. And so the verification relation now only is really just a relation over the ring that we can compute easily. And now Labrador is really suited for this because we have a linear equation that has to map to 0 when evaluated at the witness, and I have some like norm check on my witness. And when you think we're done yet, then I have to say, no, that was actually the moment when all the fun started. And I really have to stress here that our choice was, and you can discuss whether this is a smart choice or not, we really wanted to stick with the Falcon design rationale and the parameters of Falcon. So we really wanted to have a way of aggregating Falcon signatures conform with the Falcon standardization. And the first thing is that, as I said, we have this seed R. This is what Falcon has. Falcon is a randomized version of the GPV signature. And we don't want to have the random oracle evaluation within the Labrador proof system. So because we did this choice of moving the seed out of the witness, we obtain linear proof sizes, because now our aggregate signature will also contain all the seeds. If one goes away from our choice and would allow Falcon to be either deterministic or synchronized, so deterministic means there is no salt anymore. And maybe, there was Martin's talk yesterday, and he said, everyone warns you, you should of no way use deterministic Falcon, because if you get 2 signatures for the same message, that's bad. And then he argued maybe it's not too bad. Well, maybe that's an application. And in the synchronized version, you replace the fresh random seed by just a timestamp. And by ensuring that you're only aggregating over the same timestamp, you also avoid problems here. And yes, and then if you do go to deterministic and synchronized Falcon, then you can now benefit from the full power of logarithmic proof sizes of Labrador. And yes, the other thing is that we stick to Falcon, so we are given a modulus. Falcon modulus is 12,289, and you cannot change it. But if you want to use this very same modulus to work with Labrador, then you simply don't have enough room to work. So Labrador, I haven't really explained how it works, but it's like a complex proof system that resembles a bit bullet proof type system. And it has, for instance, Johnson-Linn-Strauss projections. And if you want to use them, you have some like constraints on how large your modulus needs at least to be. And the Falcon, even for one signature, the Falcon modulus doesn't fulfill it. So our idea is that we decouple the Falcon modulus from the Labrador modulus. So we introduce another modulus Q prime, but now we have to guarantee that smallness holds with respect to Q and not only with respect to Q prime. So we have to add additional constraints. The other thing is that Falcon comes with a fixed degree. Depending on your security level, it will either be 512 or 1024. And this is much larger than the original Labrador parameter sets, which was using a degree of 32. And so we ended up with pretty large proof sizes, and we're kind of baffled a bit why our proof size is so large, until after discussing with people like Khan, we figured out that actually degree is the main reason why our proof sizes are so big. And then we could use existing tools to go to subrings of smaller degrees. So our final parameter setting will actually use degrees of 64 or 128. And there's actually much more in the paper. I guess the most important proof piece, but it's not so relevant for my talk today, is that Labrador, as published last year at Crypto, doesn't come with a non-interactive knowledge soundness. So it was only provable secure as an interactive argument of knowledge. But then it wouldn't help us to get a non-interactive aggregate signature. So we had to make a lot of work and energy, to put a lot of energy into making the non-interactive proof of Labrador. And because Labrador is so complex, it wasn't trivial. You cannot just apply Fiat-Shamir. You want to apply Fiat-Shamir, but yeah, you have to be careful whether it works or not. And then other things were that the witnesses we have, so the signatures will be our witnesses. If we would do the naive way, then we would have many, many witnesses. So a big multiplicity, what I said at the beginning, but only of very small dimension, just 2. And it turns out that Labrador works best if the witnesses at the beginning are kind of balanced out between the number of witnesses and their dimension. So we do some rearranging there. And as I also said, Labrador, or I think I haven't said it, but the family of Labrador only checks the sum of the norms. But in order for the signature aggregation, we actually need a check on every norm and not only on the sum. So we also have to work a little bit harder to get exact norm bounds. So I really encourage you to go to the ePrint and check out the details there. But I guess what you all were waiting for were some numbers. And I can show you some numbers. So the first thing is that they are not yet updated on the ePrint. I'm very sorry. We want to do this until the end of the week. So the numbers I show you today are not the ones you find on the ePrint. But the ones I show you are the right ones. And everything I show you are estimates. So we haven't implemented it yet because we were waiting for an implementation of Labrador that was promised to us. And I think it's really on the way of being published soon, the implementation of Labrador. And then I think it makes sense to implement our aggregate signature. Another thing before I detail out the numbers is that all our parameters are set up for a maximum bound of signatures of 10,000. If you want to use our thing for more, then we cannot provide security anymore because parameters are set such that module sys is hard with respect to this upper bound. If you want to use Labrador to aggregate Falcon signatures with much fewer number of signatures, then I think our parameters are a bit too big or unnecessarily big. And then I would encourage you to reset parameters or redefine parameters for a much smaller n. Okay, and now our comparison. So there are not so many working aggregate signatures out there. And one of them is Phoenix, that is going to be presented on Thursday at Post-Quantum Crypto of the conference. And they are aggregating hashed and signed signatures, but they use the Michancho-Paike trapdoor sampler. So they don't work for Falcon. They only work for Falcon type signatures. And if you use the two points of number of signatures, 500 and 1,000, then you can see that we are at least one order of magnitude, I guess 2 order of magnitudes smaller. And so we are getting like 93 and 120 kilobytes. And I guess another point is that the Phoenix signature is larger than Falcon signature. Even like the single signature is larger than the Falcon signature to begin with. And so just some like more numbers, our aggregation starts to be better than the triple concatenation starting from roughly 100 signatures. And if n goes towards infinity, we get to a 0.06 compression rate. And as I said at the very beginning, answering Eamon's question, we don't get towards 0 for infinity because we have linear size, but the salt is only a small part, so it actually gets to very small constant here. And one more data point. So this is the same table I showed you before. It just moved a little. And the last table I have for you is what I said at the beginning. If you would go away from our design choices of sticking with Falcon as it's going to be standardized, you can use the synchronized version of Falcon where you replace the seed by the timestamp. And then you don't have to send the seeds. So you're really getting logarithmic. And then you can see that the proof sizes are even more interesting. So now we can go down to 89 kilobytes. And then we can compare with the other existing synchronized aggregate signature on lattices, which is Chipmunk. And then we actually beat them also significantly, which was very good news to us. And I guess this is the last slide. So related work, I think I should have done it the other way around, but now it comes. So if you do interactive aggregation, which I've completely omitted it today, there are solutions for dilithium type signatures. We sometimes also call it multi-signatures if the people sign the same message. And that was the question by Thomas. So we have sequential half aggregation of Falcon type signatures, but they get slightly better compression rates as our sequential half aggregation, but still not crazy well. And the other two papers I already mentioned are the synchronized aggregate signature of Chipmunk and the non-interactive aggregate signature using the Michanjo-Picot trapdoor sampler, which is going to be presented on Thursday. And one recent ePrint update, I have to say, was that one idea that might be interesting, and I can understand where this comes from, is that you might not want to start with Falcon. That kind of limits you in your choices, but you might start with a Labrador friendlier signature that maybe doesn't have a random oracle or that has larger modulus, and then you don't have to do all the additional modifications we had to do. And yeah, I guess this last part is not so true anymore. I'm not in Oxford, but you're still free to write me an email and ask questions. And before I end the talk, I just wanted to say that our group in Montpellier is actually hiring PhD students and postdocs. And so there are people in working on lattices and class groups and threshold cryptography.
Katharina?
Yeah.
It got freezed in the room for 20 seconds. Sorry about that. Can you restart the last 20 seconds?
Yeah. Where did it stop?
Yeah, basically the part about the postdoc, I think.
Yeah. Okay. Well, then I just wanted to say that we are searching for postdocs and PhD students, and that I'm working on lattices. Fabien Laguillaume is working on class groups. And both of us, we are working on threshold cryptography, and there are also people working on codes and computer algebra. So that could be an interesting combination. And I guess besides having a very nice team to work with, Montpellier is also a very nice city with sea and nice old town and a lot of sun. And I guess that's the end of my talk. So thanks for listening.
We have a bit of time for questions.
Thanks a lot for a nice talk. I guess this relates to the setting in which you need to reveal your seed R. The problem, as I understand it, is that you are making your verification equation into the next relation, and therefore you need to prove something about the random oracle. I guess that, have you seen these this ISIS-F assumption in which you replace the random oracle with some kind of linear function, which is easier to make arguments about, which might mean you don't need to reveal this seed R. Does that make sense?
Yeah, I think there was I'm not sure if you're referring to the work some years ago where they had like, does the Fiat-Shamir transform really need random oracles? And they replaced it by like linear functions and yeah. So
It's the synonymous credentials paper by
uh,
Jonathan et al. They call it ISIS-F because instead of a random oracle, they consider an arbitrary function f as creating your target for then pre-image sampling.
I see. No, yeah, you're right. Yeah, that would, I guess, yeah. So that's what I say. You can. That's what I meant with this last point. You can use Labrador friendly as signature. So if you don't have a random oracle in your verification, but you might be happy to use non-standard hardness assumptions.
Sure.
Yeah.
I guess he wants to stick to the Falcon spec, so that makes sense. Yeah.
Yeah, I mean, the whole point was staying to the Falcon specs, and yeah. So I guess you can make your life easier if you don't do.
Sure. All right. Thank you.
Okay, we have a second question. Yeah, give me a few seconds.
Hi again. Thanks for the lovely talk. There are other signature schemes based on beautiful birds, like hawk perhaps. And I was wondering if I understood the pipeline correctly. So you take a hash and sign signature scheme, and then the most difficult or perhaps most technical thing is finding a nice argument of knowledge that can deal with checking verification that also has this non-interactivity argument of knowledge property. But if you can do that, then this works sort of generically for any hash and sign signature.
Yeah, I think so. I mean, so if you have a hash and sign signature that is not working over ring mod q, and you don't have exactly the same mathematical objects, then you might need to go over this like generic framework R1CS. So you express your signature verification in R1CS, and then you can translate it to Labrador. So Labrador actually handles all this. So your only job will then be to translate it in R1CS.
Indeed, but being able to find a sort of any proof system that handles the verification like more natively than this conversion would, I guess, be more efficient.
Yeah, actually, we always thought that, and then we did the computations. We still think it's better to do it natively, but it's not so obvious. You really do it like there are some like nice tricks when you work with R1CS. So I guess it really depends on your signature. Then dig deeper into the literature of R1CS and what you can do there, and try to find the argument of knowledge that is maybe better natively or not, and then compare.
Brilliant, thank you.
Okay, I see. Okay, one last question.
Could you comment on why this argument of knowledge approach fails for dilithium, or have you not tried that?
I haven't said it fails for dilithium, but the thing is that dilithium uses the random oracle, also uses a random oracle, but in a slightly more involved way, let's say, because in the middle of the signature, you compute first your commitment, and you use this to put it into your random oracle, and then you derive your challenge to compute the response. So it's not clear to me how you get out the random oracle there. So the trick, then you would need to. What would it mean? You send all the commitments, maybe, but even no, I'm not sure. Yeah, I'm not sure. I think it doesn't work. You cannot just do this trick of saying, okay, I append the seed to the signature and interpret the outcome of the random oracle as my target.
Okay, thank you.
All right, let's thank Katharina again.
Thanks for the remote audience.